Hi, we are the Carleton Planetary Robotics team, and this is our System Acceptance Review submission for URC 2026. Last summer, CPRT competed in both URC and CIRC, placing 23rd and 3rd respectively. With competition learnings and requirements in mind, new and iterative ideas were brought from conceptual design to final product through design reviews. Through community outreach events, CPRT ensures membership growth alongside rover development. Our subteams have developed an integrated and tested system, which we are excited to showcase to you today. It is my pleasure to introduce our 2026 competition rover, Eileen.
Seeing that our rover performed well mechanically in previous competitions, the mechanical team was able to pinpoint specific areas for improvement. The team iterated on and redesigned all the arm and chassis subsystems with the primary goal of increased reliability and improved overall capability.
The chassis redesign focused on improved traversability and enhanced maneuvering capabilities. The team developed a four-wheel drive downed rocker suspension with a transfer bar to ensure stable driving and shock absorption. Rotary gearboxes are used to give each wheel independent steering capability. This is paired with our control system to allow for strafe, orbit, arc turn, and zero-turn movements. Continued development of our multi-infill TPU 3D printed wheel has produced a lightweight design with improved traction on Mars-like terrains. The wheels are paired with a brushless drivetrain that offers increased speed for movements and torque for traversal.
The electrical team focused on redesigning our power architecture with reliability and system protection as our main goals.
Our custom power distribution board was redesigned to allow for enabling and disabling of individual power rails. An E-fuse on each power rail gives undervoltage and overvoltage protection. To reduce space, we integrated a servo controller, CAN transceiver, and fan speed controller into the power distribution board.
Our new 6-degree of freedom arm mounts centrally on the chassis for maximum stability. Harmonic drives at the shoulder, elbow, and wrist joints deliver the necessary torque to lift target payloads. Combined metal plates and box tube create a low backlash joint, reducing unwanted deflection. Our new rack and pinion end effector allows the performance of precision tasks. End effector mast and PTZ cameras assist the operator in performing dexterous maneuvers. Compliant TPU fingers adapt to various objects while maintaining a secure grip.
Inverse kinematics control utilizes the move it solver, translating task space coordinates into joint space configurations. This guarantees the high precision required for operations like USB insertion. For efficiency, operators can also record and execute custom joint trajectories, such as a compact stow state to a single macro command. Finally, our autonomous typing pipeline fuses this kinematics control with computer vision, dynamically mapping target coordinates and calculating inverse kinematic solutions to actuate specific keystrokes entirely without manual operation.
This year, the software team focused on reliability, increased telemetry, and situational-based control.
We have moved to a 900 MHz communication system for longer range operation. A custom automated tracking antenna allows for higher gain antennas while always operating in the main lobe. For video streaming, gradual decoder refresh, adaptive forward error correction, hardware-based decoding, and more manual controls were added, balancing image quality, latency, and reliability based off of current network conditions. During a real-life test, these improvements allowed us to travel 1.2 kilometers away through areas without line of sight in a noisy urban environment, a 70% increase over last year. Our modular and customizable web UI provides the telemetry data needed to accomplish tasks and diagnose issues quickly.
Our autonomy models terrain at 18 Hz, 10 times faster than last year. Stereo vision maps slope and roughness 10 meters ahead, while satellite LiDAR data precedes the map for beyond line-of-sight planning. Using these maps, the planner navigates to GNSS waypoints, detects Ruker tags, and avoids obstacles. RTK-corrected GPS provides centimeter-level positioning. Object recognition uses YOLO models trained on over 10,000 images, achieving near-perfect accuracy on URC realistic datasets. The system also has the capability to autonomously run search patterns.
A quadcopter drone was developed to assist the rover during the 2026 delivery mission. Our custom-designed chassis, PDB, and flight computer are going through flight testing to support the rover in aerial scouting and object marking.
The science model was completely redesigned to improve the stability and reliability. We collect a 5-gram sample using a centrally mounted carbide-tipped hammer drill lowered by a dual lead screw system. At depth, the sample is captured in our collection disk. From there, soil is distributed to the ACLSA and the magnetic stir tank. The mixed solution is then sent for full analysis.
The full analysis includes a humidity sensor, a microscope to provide a close-up view of the sample, a suite of strip tests which use the solution from the stir tank, an HCl calcium carbonate test with a camera and a sensor to detect CO2, and a custom-made polarimeter equipped with a transimpedance amplifier with a refractometer for sugar concentration to measure homochirality, sugars formed through biotic processes.
Thank you, and we hope to see you in Utah.